I'd like to welcome everybody to this next presentation in the series of Community of Practice webinars. The Risk-Informed Performance-Based Principles and Policy Committee, RP3C we call it, of ANS, has been putting on these events for the past 5 years. Presentations and recordings of the events are available to the public at the ANS website under the tab RP3C. There are now over 50 such recordings available. The purpose of these webinars is to offer practitioners of concepts and methods related to risk-informed and performance-based approaches, RIPB we call it, a chance to share their knowledge and experience. I would expect that such practice is associated with implementing nuclear technology and evaluating its safety and effectiveness. The purpose of RP3C is to help modernize ANS standards. The Nuclear Energy Innovation and Modernization Act, NEMA, of 2019 associated modernization with application of RIPB approaches. Later, the idea of using RIPB to achieve effective regulation and oversight of nuclear technology was addressed in the Advance Act 2024. More recently, concepts of modernization have been emphasized in the Executive Order 14300 and others. There is growing realization within the nuclear community that conventional, prescriptive, and deterministic approaches are not going to support increasing use of nuclear technology to play its rightful role for the benefit of society. Socializing alternative approaches could drive changes in industry and regulatory practices. ANS offers the COP files on its website to serve as a knowledge repository of the experience from a wide range of practitioners in the field. We hope that more people will use this knowledge base to speed up needed changes in the state of the art as well as the state of practice. These events are generally scheduled for the last Friday of a month. Today, we'll hear from Craig Benson, who will be talking about something that is not usually the subject matter of our COP topics, but I think is an example of how performance-based approaches have such a wide application. And I look forward to hearing Craig Benson give us the presentation. Craig, please go ahead.
Great. Thank you, Prasad. I appreciate it. I am going to post my PowerPoint. All right. I assume you can see that, and then I'm going to put it full screen mode. Hopefully that's okay. And I'm going to use the laser pointer. Does everything look good? Can you see it on your end? Somebody want to confirm? Great. I'm probably not your conventional ANS presenter. I'm an environmental engineer, a geological engineer, a hydrologist, and I work on the back end of radioactive waste operations, largely in mill tailings disposal facilities or low-level waste facilities or mixed waste disposal facilities. I work on that essentially end state of our materials. And all of those systems that we deal with today are all developed, all of those disposal facilities for those materials are designed and implemented based on a risk-based, performance-based approach. And so what you've been talking about in your group is very relevant to what we do as well, at least from a practice side of things. What I'm going to talk today about is an aspect of that is we develop a model, we do our simulations, we develop performance assessment, but then we need to actually prove that all the work that we've done actually can be realized in the field. And this particular case that I'm going to describe, which started in the 1990s at a time when there was a great deal of skepticism about whether we could actually make predictions and could develop conceptual designs, make predictions that they would actually be borne out in the field. And so at that time, there was a great deal of skepticism, and there was a real need then to validate what we had in our performance assessment with full-scale field data. And that's what we're going to talk about today as an example of where that was done. And what we're going to talk about is a field monitoring program that went for 22 years at the uh, Monticello Uranium Mill Tailings Disposal Site in Monticello, Utah, and particularly looking at the water balance final cover that's placed over the waste at this site. The waste disposal unit relies on a natural system type of design for the hydrologic containment. And we're going to talk about how we demonstrated that design would function as anticipated and predicted in our performance assessment modeling. So that's some background on what I'm going to talk about. It's probably a different topic than what you're commonly hearing about in many of these webinars, but I think the threads that are in it apply to lots of different applications. Just a little bit of background on me as well. As I mentioned, I'm an environmental engineer, a geological engineer, a hydrologist. I'm somewhere between those. I spent the 25 years in the early part of my career at the University of Wisconsin-Madison in civil and environmental engineering, geological engineering, and then in 2015, I became Dean of Engineering at the University of Virginia, where I did similar types of research. And I'm actually now emeritus at both of those organizations. And by emeritus, that means that you can, one, work for free, and you can keep your email. That's what being emeritus means at a university. So you can work for free. And most academics do that. And I have to admit, I'm one of those. So let's talk a little bit about where this all comes from. I'm part of an organization called CRESP, the Consortium for Risk Evaluation with Stakeholder Participation, which is an organization of universities that provides translational research for the U.S. Department of Energy Environmental Management Group. And what we do is essentially provide knowledge that goes into making decisions that EM needs to work on a regular basis. We're a collection of universities, each of us with our different expertise. And my part of CRESP is called the Landfill Partnership, where we focus specifically on disposal facilities, like the one you can see here in the photograph on this slide. I'm also involved through CRESP in a similar community of practice called the Interagency Performance and Risk Assessment Community of Practice. This is essentially hosted through DOE Environmental Management, but is open to any of you. And I would encourage you, if you have interest in the disposal side of things or the remedial action side of things, that you consider participating in the DOE EM community of practice. It's open to all, to anybody in the public. And there's lots of great presentations that are all for free. So I would encourage you to look at that if you have an interest. I've been fortunate to be the co-chair of that that community of practice now for a couple of years, and it's been really, really interesting. Finally, before I really dig into our work today, I want to acknowledge some other people. All these projects, particularly those that go on for decades, have lots of different people involved. This one in particular, Jody Waugh, who's a colleague that I've worked with for years, who's DOE Legacy Management. He's a rangeland ecologist, and still he's retired, but like me, still working on these things. And Jody and I are actually working on a really interesting paper on this particular project right now. Bill Albright, former hydrologist from Desert Research Institute, Bill's emeritus as well, and is a colleague that I work with quite a bit still. And he's was integral in this study. Preechap Awantragoon, who's from the Thai military and their academy, their university. He was one of my former PhD students. He's done a lot of the data analysis for this work. And then Aaron Tiger and David Holbrook from DOE Legacy Management have been involved in collecting a lot of the data over the years, out in the field helping us out. So I just want to make sure I acknowledged all those. So let's dig in now with that background about me and others and where we're coming from. We've been fortunate to have the opportunity to instrument and examine the field scale performance of covers over containment systems in the Colorado Plateau at 3 different locations. The one I'm going to talk about today is just one of those. They're in this part of the United States which is rich in uranium mines and also historic uranium mills and mill tailings disposal sites. And as we've learned more about the disposal facilities, there's been need and interest in instrumenting them to gather information about how they actually behave, as opposed to the way they are planned to behave in models. 3 of them in particular, though, the Grand Junction disposal site, the Monticello disposal site, these are both DOE facilities, originally constructed through DOE EM and now managed by LM. And then the White Mesa Mill, which is actually just down the street from Monticello, which is the last active uranium mill in the United States right now. And we actually have a field study at their tailings facility that has a lot of similar attributes to what we'll be talking about today. And all 3 of these have had unique aspects to them, but the field monitoring has been integral in essentially proving out the PA that was put together. But we're going to focus here on Monticello as we go forward. Let's talk about where this comes from. This is the town of Monticello, Utah, and at the top of my slide here. It's a wonderful small town, about an hour and a half south of Moab, if you know where that's at, in Utah. And during World War II, it was the host to a uranium mill that processed uranium ore and produced uranium for use in the weapons program. Like many of those mills at the time, the tailings were just essentially dumped on the ground when the processing was completed. And if you're not familiar with what tailings are, we take rock that has uranium in it. Pitch blende is the name of that rock. We grind it up, we put it through a chemical solution to extract out the uranium, and the remaining stuff, which is a ground up rock, fine particles, still radioactive, had lots of other constituent with it. That's called tailings. This is fine textured soil-like material with lots of contaminants in it. And in the good old days, as we might call it, those were just dumped in a pile outside next to the mill. Didn't know that wasn't a deliberate mistake. It was just didn't really understand the consequences. In fact, some of those materials were considered valuable and were used for construction in the town of Monticello and many other mining towns in this part of the country back in that period in the 40s, 50s, and early 60s. All of that material, of course, was radioactive and has now been removed. But the tailings were largely spread in this valley here, which was also had a stream bed down the middle of it, and groundwater became extensively contaminated as a result. And in the 1990s, there was a corrective action undertaken to exhume all of those tailings and also undertake groundwater restoration in this particular area. And all the tailings that were stored in this area were excavated and then placed in a disposal cell just nearby. And if you come down US 191 through Monticello, from Moab down to Monticello and further south, a pretty common US highway, and look off to your left when you're going south, you'll just barely see this in the background. You never even notice there was a large mill tailings disposal facility right there. But it was a 32-acre facility. It's lined, and I'll show you that in a minute. And it has a cover system on top that was at the time was very innovative, and I'll talk about why that is. But we're going to focus on this disposal facility, and particularly this green triangle right here. Just a little bit of background, though. This is the disposal facility. That's the test area. And this green pond over here is actually where the leachate from that disposal facility is evaporated. That's a treatment pond as well. Always kind of amazed me that we had a uranium mill tailings leachate pond that was evaporating just on site. But it is a site that is has containment, so it's not a hazard. What does this disposal facility look like? This was designed through a performance assessment at the time with the intention of limiting releases so that a dose criterion at a point of compliance, which is near the property line, would be maintained at all times over a 1,000-year period. And the facility that was designed using a performance-based approach looked like what I show. It looks like what I show here in this figure. It's got tailings that are stored within it, and the base of it has what we call a double composite liner, which means that it has two different liners, and each one of those is a composite system created from a thick, heavy-duty plastic sheet called a geomembrane or GM, underlain by a thin factory manufactured clay barrier called a geosynthetic clay liner. And these two things, when put together to create a composite barrier, they work synergistically, are extremely effective in controlling leakage. And when we put two together, stacked with a leak detection zone between them, they become very, very effective. So we've got this really robust liner at the bottom that prevents releases out of the facility. But it prevents, but I should say limits releases, because no liners are 100% leak free, and they all have discharges to the environment. And while this system is operating and the tailings are draining down, leachate is being collected in the base through these collection pipes and pumped out for treatment in that pond that I showed in the previous slide. The leak detection system between the liners is being pumped out and evaluated in the context of what's an acceptable leakage rate. And these are active processes. But this facility isn't going to be around for just 10 years or 20 years or 30 years. It's going to be around for 1,000 years, maybe 2,000 years. And we're probably not going to be pumping leachate out of this facility for 1,000 years. And we're probably not going to be actively maintaining this facility even after 100 years. So while we have all these barrier systems in the bottom, which are made out of synthetic materials and pumps and pipes, ultimately we're going to walk away from this, and we're going to have to rely on other things to provide environmental containment. And that's really where the cover comes into play. During this active period, we pump and monitor and treat the leachate, but at some point we are going to walk away, and we're going to need a cover on top that limits the amount of water that will get into the tailings and generate leachate over time to a sufficiently low amount so that when there are releases from this facility, we maintain a acceptable dose at a point of compliance. So the cover over the long term has a really, really important role. It is the predominant environmental control system in the long term. Short term, it's the liners, it's the pumps, it's the treatment systems. But long term, everything's about controlling how much water can get into the facility, which ultimately ends up being how much water can leave through the base. So the cover is thought of as the most important aspect of the complete design over the long haul. And so it gets a lot of scrutiny as well. Now, we developed this design, as I indicated, in the 1990s. And at the time, the whole development of final cover systems and barriers was evolving. There was a great deal of debate about what would be most effective at this site over the long haul. There had been a great deal of work done at Hanford on the Hanford barrier, which has many analogs that we'll talk about here today. There, outside of the Hanford barrier, there wasn't much in terms of evidence similar to what we're going to talk about here today that these type of systems actually worked. And the thinking was that rather than design a cover that was made largely out of geomembranes and clay barriers, like I showed for the liner, let's create a system that emulates and is congruent with the natural environment. create something that simulates the natural environment. And in this environment, the hydrologic system is adapted in such a way that the amount of deep drainage that comes through a profile is nearly negligible. This is a semi-arid to arid location in Utah. At this particular site, it gets about 14 inches of rainfall a year. So it's a dry site, and in arid and semi-arid regions, the hydrologic system in the near surface has essentially evolved to maximize storage and capture and use of all water that lands on the ground surface from precipitation. So that was the basic idea, to create a cover system that replicated and was congruent with a natural hydrologic environment. And we had to do that with this so-called water balance cover, which has a number of different layers here. And I'll just talk through these. We have this gravel admixed layer at the top. There's a mixture of fine textured soil and gravel, which is meant to provide erosion protection at the surface, but also provide capillary continuity with the underlying materials. A fine textured soil for water storage, a animal intrusion layer beneath that, and then another fine textured layer for additional storage, and then a capillary break at the bottom. And that's a little trick we do in hydrology. We put a coarse textured material under a fine textured material, and under unsaturated conditions, that it boosts the capacity of this fine textured material to store water. We call that a capillary break. But the idea here was to create a system that would store water within this profile with limiting releases out the bottom to trivial amounts, store it during the wet period of the year, and then release it to the atmosphere during the dry period of year. And do that in a way that the percolation or the drainage from the bottom of the cover would not be more than 3 millimeters per year on average over its lifetime. That's a minute quantity of water, 3 millimeters per year. But in arid and semi-arid environments like we have in Utah, that's what happens in the natural system. There isn't direct recharge in vegetated landscapes like this. So can we create something that simulates the natural environment, has the same level of hydrologic control? And the beauty of that is if we can create a system that emulates or mimics that natural system, it's going to persist because it's congruent with its surroundings. When we take plastic barriers called geomembranes and geosynthetic clay liners, put them in near the surface, from the day we put them in, nature starts breaking them down. This system is congruent with nature and is specifically intended to work with nature to achieve the objective. And so instead of breaking down from the day you build it, it actually gets better over time. And we'll see some of that. How does this work? It's actually really pretty simple. We take that cover profile as a thick layer of fine textured soil that acts like a sponge. Precipitation that falls from the sky, lands on the surface, it infiltrates, and that we hold that water in the sponge. And that sponge has a certain amount of capacity. And if that capacity isn't exceeded, percolation out the bottom is negligible. On the other hand, if it is exceeded, we'll get drainage out the bottom into our underlying waste. And what we do is essentially look at balancing the hydrologic cycle that occurs throughout the year. We know in the fall and winter, which we're entering right now, the days are cooler. We tend to get less intense but more frequent precipitation. We have less energy available in the atmosphere to evaporate water. And so we see at this time of year, soil profiles tend to accumulate water or storage, soil water storage. That's essentially the amount of water stored in the profile. It increases. And then when we get out of winter and into spring, days are longer, temperatures are warmer, we've got more energy from the atmosphere, we've got plants starting to emerge, in that water that's stored in the profile is extracted through evapotranspiration and the storage drops off. The sponge begins to dry out. And we do that each and every year. The sponge gets wet and then the sponge dries out again. And that the flip side of that is, where is that water going? It's going back to the atmosphere via evapotranspiration. The plants are removing it and sending it back to the atmosphere where it came from. And the trick is to make sure we have a big enough sponge to manage the precipitation in our environment. If we keep our storage within the profile below the capacity, percolation at the bottom is trivial. And that's really what we were trying to do with the cover at Monticello, was design a system like this that would mimic the natural system and achieve these objectives. Now, they're never quite this simple, but this is what our objective was for this particular site. The plants are really an important part of this process, as I'll talk about. The plants are like straws that are connected to both the atmosphere and then penetrate down into the soil profile and allow us to pull water out of the soil profile and send it back to the atmosphere. They're essentially like straws with little pumps that pull the water out of the profile. And it does that by a gradient in water pressure that's along from the leaves, where it's very negative, down to the root system where it's less negative, pulling water up and transmitting it to the atmosphere. And it's exchanging that water from the plant leaf surfaces for carbon to build the plant. So that this exchange of water that's stored in the profile for carbon in the atmosphere is what builds biomass and creates a vegetative community. So we actually have a natural system that's doing all the pumping for us in the environment to remove that water. But it's our job to get that system started and create an environment where it can thrive on the surface of that cover. At the time in the 90s when this was built, were all really neat ideas, but there's a lot of skepticism about whether you can actually do it. There's a PA that was done at Sandia. There's lots of modeling, lots of predictions, but we're talking about limiting this percolation at the bottom to 3 millimeters per year based on this concept of storing and releasing the water. It sounds very academic. Can you actually prove that it'll work? And that's what we went about doing. When we built the Monticello disposal facility, we took a portion of the cover at that facility and we built the world's largest so-called drainage lysimeter, this triangular area right here, where we monitored precisely how much water drained out the bottom of the cover profile, the key variable in our performance assessment that had to meet 3 millimeters per year or less to be successful. And we also instrumented this system with a series of nests of instruments to be able to examine, is that cover profile functioning the way we expect? Is it wetting up and then drying out? Are the plants doing their job to extract the water? And how does that vary as the plant community varies as well? So we built this very large lysimeter, and I would say in part it wasn't done necessarily because it was interesting, but really to prove out the idea that uh, we can actually design a system like this and meet our performance goals, and we're going to prove it with data. I had one of my EPA clients early in my career who had a simple saying, data are good. And that's exactly what we were going to do here. We were going to monitor the hydrology of this entire system and prove that it works. And that's what we did. When we were building this, and we instrumented it too with a series of sensors in the profile to measure water contents, matrix potentials, temperatures, all the key state variables that affect the hydrology. This is just some photos. These are actual photos. They were actual film. They're not digital. I scanned them in later in life. But this is actually the cover being built at Monticello back in the late 1990s. As I indicated, there was some consternation about whether the system could actually work. And so while we had designed that entire profile to be to function like the sponge that I mentioned, there was enough, let's say, I'm trying to think of the right word, but there wasn't enough confidence that actually it would work as well as we had proven or as we had proposed. And so a compromise was made. Okay, you can build that cover, but you're going to have to put a traditional barrier down in the bottom. And if you look closely at my slide at the bottom, at the very lower part of our profile, it has a geomembrane and a clay barrier below it, which is a conventional barrier system. So this actually has the natural system type cover on top. But then they said, okay, you can do that, but make sure you put a the barrier system for conventional cover below it, just in case it doesn't work. And so there was this geomembrane at the bottom of our cover, and we're thinking, this is a great opportunity. We can take this geomembrane that we've agreed to install and use this to build a monitoring system to look at the full-scale hydrology of this system. So this black plastic sheet, this is high-density polyethylene geomembrane, put over the subgrade at this site. That's directly over the top of the waste. And we built in these flaps in that geomembrane that allowed us to route all the water that emanated from the bottom of our water balance cover and collect it and shuttle it to a sump where we could send it out in a pipe and meter it to determine what the percolation rate was. And that's what I'm showing here. This is the flap that went up vertically into the profile that was built. And all these welds were very carefully tested to make sure that they were leak tight and that we were getting high quality data. We would collect all that. It came to a collection point into a sump, and then it actually was routed through a section of PVC pipe and then into collection basins where the water would be collected and where we could meter it very carefully. We did that both for the percolation that came out the bottom, but also the surface runoff as well. One of the things I think we've learned over the last couple of decades is surface runoff predictions are always over predicted. And we learned a lot about how much we can trust and how much we can't based on measuring surface runoff as well. In the profile as well, we measured all the state variables, temperature, matrix potential, water content, with a whole suite of sensors, which at the time were really pretty new and innovative. They're pretty almost standard practice today, but at the time they were all really new. These tanks that we have to meter the flows, we wanted to make sure that we got very precise data. So we actually have a triple redundancy monitoring system that uses 3 different techniques to monitor the flow, different essentially physical principles, and with different levels of precision. And we compare each of those different measurements each month in tremendous detail to make sure that they're in alignment. If they're not in alignment, we go back and figure out why. So these are very sophisticated systems to meter those flows with a high degree of precision, because we needed to have extreme confidence in what we were measuring to document that actually worked the way we expected. These systems also, they're out in the middle of nowhere. They have to be able to function on their own. So these tanks fill up. We had those essentially self-drainage systems, these things called a flouter, really nifty. They allow tanks to fill and drain completely with no valves, no mechanical parts, completely in remote systems. This was essentially autonomous on its own. All equipped to a data logger with cellular telecommunications, where we could look at it back in our office and control it back in our office if we needed to. But the key thing here is a lot of redundancy using different techniques to make sure that we had high degree of confidence in the data we were measuring. We could prove that the data that we were collecting was accurate. We didn't only measure the hydrology, we looked at the ecology as well, particularly the plant community that developed, because that was important as well. But what did we find? Wow, it was just remarkable. It worked better than we could have expected. This is a water balance graph. It has cumulative precipitation and evapotranspiration on the Y1 axis. And over on the Y2 axis has percolation, soil water storage, and surface runoff. So we've got the flux on the surface, the water drainage out the bottom, percolation, and the soil water storage, which is the total amount of water within the profile, or the water contained in our sponge. And you see a couple things in here in this graph. One, we started this at the very end of 1999, and we went all the way out to 2022. Who gets to do an experiment that long? That was just cool in itself. But you can see that when you look at this graph, that it did exactly what we expected it would do. The water would accumulate in the cover. The soil water storage would build up, and then in the spring, the system would dry back out as the plants removed the water. And it varied from year to year. Sometimes it didn't wet up very much, depending on how wet it was. Sometimes it wetted up an enormous amount, but then it recovered again. The plants extracted all that water. We are also able to show that our percolation rates were extremely low. less than 10 millimeters over the entire monitoring period. 0.4 millimeters per year was our long-term percolation rate. Essentially, with this natural system approach, we look at this graph here, the blue line is cumulative precipitation that fell onto the site during the record period, and evapotranspiration is the water that was returned to the atmosphere. They're essentially congruent, except for this little short period here. Outside of that period, those two lines are congruent. Almost every bit of water that fell on this system was returned to the atmosphere. A little bit came out of the bottom at percolation. A little bit was shed as runoff, but it's pretty flat and it's got a pretty rough surface. Most of that water infiltrates in and then goes back out. It worked just like we expected. When we look at the precipitation and percolation, we found during the record period, we only had 5 years when we actually got percolation. We only had 5 years when we had percolation transmitted, when the sponge capacity was exceeded. Some of those years were pretty significant, like the one I mentioned in 2005, where we actually had so much drainage out the bottom that the drainage out the bottom of percolation continued into the following year. We call that a carryover year, or C. When we had 3 out of the 5 years, we had a slug of water come through, and then it would just slowly drain out the bottom, and it drained over such a long period of time that it actually extended into the following year. But it worked remarkably well. The percolation rates periodically were exceeded. The storages periodically exceeded, and the percolation rates were non-zero during those periods of wetter times. And we look at our water content records. This is a very busy graph. I'll just talk about this at a high level. But we see that same thing that we saw in the storage curve, where it's going up and down. And that's what this graph shows here. That in our cover profile, which is a whole series of layers from surface, upper storage layer, middle storage layer, a biota intrusion layer, a lower storage layer, and then the sand layer. And each of these layers down through the profile, each year the water content would go up, and then it would go down, up and down. So it's storing the water and then be extracted to the surface. Now, one way we can demonstrate that it is actually being extracted and returned to the surface into the atmosphere is by measuring the percolation rate. Even though these water contents go up and down, we saw very little water ultimately come out the bottom of the system and flow to our monitoring points. What we also found is that it did function as we anticipated. If we looked at just the upper parts of the profile, that each and every year, the water contents in each of those different units would return back to their essentially baseline condition. So it would wet up, but then the vegetation would pull all that water back out and bring it back down to essentially that dry state. And you can look at the water content here is 0.04. That is really, really dry. The vegetation pulled out essentially all the available water, which is exactly what you'd expect in this climate. The plants are opportunistic. They thrive or die, and they will extract every bit of available water that they can find. And we saw that at each depth as well, both deeper in the profile and the same type of behavior. So it was functioning just as we expected, but now we weren't just talking about it running a model. We had the data. We proved that it was actually working like we'd expect. We looked deeper in the profile. We saw some really interesting things as well. We found if we looked, excuse me, in the middle storage layer, the biointrusion layer, it functioned a lot like what we saw at the surface, but deep down in the profile over time, it actually got better over time, and the ability of the plants to extract the water. What we found is that over time, the water contents deep in the profile actually dropped to a lower minimum in the spring months after the growing season had kicked off and water was being extracted through the profile. This was really interesting that we had a change in behavior about halfway through, deep down in the profile, that actually benefited the performance. This was not something we predicted, but something we found through collecting data. Why did that happen? Well, I mentioned we're monitoring the vegetative community. What we observed through that same period of time of change is that the vegetative community was evolving into this long-term ecosystem that we had hoped to achieve, with a mixture of both grasses at the surface, which tend to move water at shallower depths, but then deep-rooted woody shrubs, which would extend roots deep down to the profile and extract water at great depths. And during that period where I showed the water contents dropped deep down in the profile, is that same period the shrub community essentially evolved to a much greater significance on the surface of the cover. So it made a lot of sense. We weren't planning on this, but this evolution of the shrub community, where it's essentially optimizing its ecosystem by extracting as much possible water as I can get out of the profile, was optimized here. It actually dried out the base more than we anticipated. We also saw that even that, it just very episodically, we would see water drip out the bottom. I mentioned just 5 years, and we had 2 years where it was considerable, still small percolation rates, and then we had 3 other years in that period when we had smaller quantities of water come through. But just 5 years during that 22-year period when we had percolation. Really worked even better than we expected. We did find some interesting things that we didn't expect that weren't in our models. I mentioned we get water accumulates in the profile, and the storage in the sponge gets exceeded, and it generates percolation. These dashed lines are the storage curves showing the amount of water stored in the profile, and it reaches a peak. It's up at the sponge's capacity, and we begin to transmit percolation. That's the solid green line here, which shows the percolation being transmitted. We see this is percolation versus time. The slug of water come out as the sponge has been filled, and then it just drains very, very slowly over time. This is not something we anticipated. This was not in our models, but it's something we realize now has to do with the intricacies of that capillary break at the bottom of the profile. It would be, at this very higher rate of percolation for a very short period of time, and then go into this very long drain down period. We learned about that through the data that we were collecting. We look at our data in general, we found a pretty strong correlation between the total annual percolation and the amount of precipitation we would get in that fall-winter period when the vegetation was dormant and we were storing the water. What was interesting is that this really falls into two groups. Our early half of the record, where we had this correspondence between the data, and then I mentioned that shrub community developed, and we had greater water extraction at depth. And I realize this is just 2 points, but from that period onward, we're able to actually manage a greater amount of precipitation with a lower percolation rate over time. Now, I only have 2 data points. I can't prove that, but it sure seems to be the case. What's important, though, is that we're able to demonstrate that we could meet the 3 millimeter per year criterion, even under these wetter years, and with only one case in the record where we exceeded it on an annual basis, but over the long term at 0.4 millimeters per year is our annual percolation rates. So we were able to demonstrate that with a high degree of confidence. One of the things that's a challenge when we build these models is we actually have to parameterize the models and make predictions. And we never actually know how things are compared to what we build and how they evolve over time. How does nature take what we build and manipulate it to function in that hydrologic system that she has so carefully masterminded, over millennia and millennia over time? So one of the things that we did to inform kind of our future thinking was we did a lot of evaluation of the hydraulic properties of the in-service condition of this facility. And we were able to show both through these field tests and some large samples that we were able to remove and take back to the laboratory. This is also a lot of fun to be able to go out and do all this field work. But we were able to show that these systems, we build them one way, and we create specifications around that. Nature takes them, manipulates them, and changes them into a state that's congruent with that environment in which the disposal facility is located. The saturated hydraulic conductivity of the cover materials, its ability to conduct flow under saturated conditions, typically increased 10 to 100 times at the Monticello site. So it was 10 to 100 times more permeable than we anticipated during our PA. Our water retention characteristics are essentially the sponge capacity also evolved while it was in service from a very distinct set of curves here. That's the black lines here describing essentially the sponge characteristics. And then the in-service properties after years and years of service, they were different. And from this type of data that we've been collecting, we're able to make recommendations to people doing PAs is this is what you're likely going to see while it's in service 10 to 20 years out. And that's probably different the way you've been thinking about it as built or when you're parameterizing your model. So when you're building a PA model and putting forward a PA, use these recommendations to parameterize your system with something that's going to realistically represent what you're going to see in the long term. That same thing true with both our hydraulic properties, but we put all these properties in for vegetation as well. We take them out of the literature and we put them into our models. But what do we really see? So we actually did a lot of characterization of vegetation, both above ground, but below ground as well. And we're able to make recommendations to future practitioners who are doing PAs. How do we collect that data? What is appropriate data to put into your models that represent the full scale conditions over time, both for the soil properties and the vegetation properties as well. So I just wrap up here. I've got about 10 minutes left. We were able to develop a highly effective cover system. And we designed it, we ran a PA, but then we went out and we proved it. We proved that it wasn't just something in a model, but it was something we could realize at full scale. That nearly all the water that reaches the system from the atmosphere is returned via evaporation and transpiration. The amount of water that gets down to the bottom of the cover profile and ultimately would get into the tailings was actually considerably lower than what was in our PA. We have predicted 3 millimeters per year, which is actually very small in itself, but realized less than 0.5 millimeter per year. Our peak percolation rate was 4 millimeters a year, a little higher than our annual goal, but our annual goal was over the long term. But that was also early in the record before that shrub community developed, that woody shrub community with deep roots to extract things at lower depth. And that amount of additional water is about 2 or 3 centimeters of water. That makes up for that difference in percolation rates that I showed earlier in the graph. I don't have a lot of data to prove that, but I do believe that the deep-rooted shrubs drive this thing out just a little bit more, making it more resilient, increasing the capacity of the sponge a bit more, and providing us with even more lower percolation rates. And then finally, the other thing that we came out of this was recognizing that while we just do the best to create a system that's congruent with nature, whatever we put in, nature's going to manipulate it and change it. So we want to create it in a way that's close to what nature's, as close as we can to what nature's going to want to uh, live with it as, but recognize that she's going to change it, and made recommendations based on data from this site and about 25 others about when you're building future PAs, what type of parameters should we be putting into the model? How do they vary from what we're normally thinking for in-service so that they reflect the longer term conditions accurately? And those recommendations are in a couple of Nuclear Regulatory Commission reports, CR 7028 and CR 7288 have guidance on that. Okay, so you got a whirlwind of hydrology today and proving out a performance assessment with full-scale data. We got about 10 minutes left, and I don't know if there's any questions or anybody else has things
Yeah,
you'd like to ask me.
Craig, we've got,
Go for it.
thank you for this. We got a couple of questions in the chat. I think they're
Great.
actually fairly related to each other. So, I'll ask the more detailed question first, and then
Sure.
we'll come back. So the plant roots absorb a lot of the excess moisture. However, if this system is designed to last for 1,000 years, what happens if in the future the plants die out and future generations don't replace them?
Yeah, this is a really, really relevant question and an important one. When we look for when we design that design a plant community doesn't sound quite natural, but when we think about what it's going to look like, what we do to find the plant community that will persist is we look for natural analogs. We look for a natural system in that environment that has the both a similar cover profile soil wise and vegetative community that we can demonstrate has persisted over millennia and millennia. And so that's a part of the process I didn't talk about today, but we use natural analogs to identify those persistent systems so that we don't have that die out. Because if it did, if the vegetative community just went away, it wouldn't work, right? But those in those environments, they don't just go away because that environment is constrained with water availability. It has an ecosystem, and if there is water available, a vegetative community will establish itself, and it will extract that water. It's really about how do I get it optimized around the ideal community that's going to be able to remove all of the available water and achieve our broader goals. So it's probably a longer question than answer than you suggested in your question, but this role of analogs is critically important because if the vegetative community went away, it wouldn't work. So we find vegetative communities as part of the design that have demonstrated persistence in the area, at least for the records that we have, right?
Yeah, and so along those lines, and maybe slide like 19, just something with the cross section of the profile.
Let's see.
Um,
If
so
find if I
the
can
the
find 19.
question in the
Yeah,
chat,
please.
well, the one right before this that has the full profile. There you go. So the question in the chat is, what is the life expectancy of the sponge? And so I think there's, a couple different ways you could answer that in terms of, how long the design period was, how long was the performance assessment for, and then, I mean, maybe even what would be the kind of the weakest link in the profile there.
Yeah, a few really good questions there. When we design these facilities, we look at a operating life of at least 1,000 years, and then we'll often make predictions to 10,000 years or to peak dose, right? But we're thinking about systems that are going to persist for at least 1,000 years. And so when we think about that, how long is it going to function? We go back to that analog concept again. Can we find uh, examples in our natural environment of soil profiles and concurrent vegetative communities that persist over millennia, right? Over millennia upon millennia, so that we can create system that will persist over time. So we spend a lot of time trying to demonstrate that what we're going to build replicates nature, and nature has had this persisting for thousands of years. I think that gets at the question that was posed. If not, please let me know.
I think so. Steve Nesbitt, do you want to ask your question, and then I'll probably go ahead and wrap us up here.
Yeah, thanks. It kind of follows in with the last question, Brandon. Craig, great presentation. Yeah, on that 1,000 year period, I wonder if you could comment any on the choice of 1,000 years. Now, I have worked in high-level waste disposal, and periods of compliance there range from 10,000 years to a million years.
Yeah.
And for the material you're talking about here, it's essentially as radioactive 1,000 years from now as it is today. It doesn't change over that period of time, so it's not like it's less concerning. So, what can you tell me about 1,000 years and why that's what they use for mill tailings?
Um, yeah, really good question. I couldn't tell you precisely why it is 1,000, and I kind of lump bill tailings and mixed waste together because we use similar types of objectives for mixed waste and low level waste disposal facilities too. 1,000 years. I don't know where that comes from. That's in code. Like DOE 435.1 has that as a requirement. That's the low level waste and mixed waste requirements for at least weapons produced waste. I'm not quite sure where that comes from, but one idea was that it was essentially long enough beyond what was practical that it forced us to really think really hard about our designs to make sure that they were durable and sustainable. But as part of the PAs these days, early on, people just used to run them for 1,000 years, but now you run them out to peak dose, which gets at essentially what you're talking about is that I may get to 1,000 years and I'm not in anywhere near where I have to be in terms of protectiveness, right? Because I've got many, many, many more years, which I have a threat posed by the system. And so doing at least the predictions out to peak dose gets you closer to that. And that's probably more congruent with what's done in the high level waste world, but I have to admit I'm not particularly knowledgeable of that. Did
Well,
that address
thanks.
that to some of your extent, Steve?
It does. Thanks very much.
Yeah. In
Yeah.
essence, it's kind of like somebody made up 1,000 years, and that's what we've been using, to be
Well,
honest with you. Yeah.
and so for this particular setting, I think that the peak dose as the performance objective is a little bit more performance based rather than an arbitrary round number, right?
Yep.
But thank you, Craig. We are at the end of our hour, so we very much appreciate you, and also on behalf of Steve, who had to step out for a chat with the dean. I appreciate everybody else's time and participation over the year. So this is our last RP3C community of practice. So enjoy a couple months break from having to listen to my voice asking the questions. I hope everybody enjoys the spooky festivities over the weekend and has a great rest of the day. And we will call this a great success, and we'll end there.
Thank you for having me. It's nice to have an opportunity to speak to your community. So thank you very much.
Thank you, Craig. This is Prasad. Appreciate it.